Hey guys, going to talk a little bit about reaction rates today. So, when we talked about reactions, remember we've been kind of going one direction. A plus B yields AB. Well, in reality, that doesn't happen all that often, right? Usually with reactions, reactions are reversible. So this is reversible. And that's a bad one. So reactions are usually reversible. So the point at which the forward reaction equals the reverse reaction is called equilibrium. So if you think about the way we use the word equilibrium in the human language, we mean it to mean balance, right? But really what equilibrium means is two opposing rates are equal, right? So when we have balance, our desire to fall this way is equal to our desire to fall this way, right? And if two things are equal and opposite, the net is zero. So reaction rates, right, talk about where that position lies. So if we look at this concentration, or this reaction graph here, at this point right here, right, we're at equilibrium. So reactants equal products. So in equilibrium, the rate at which I'm forming products is equal to the reverse of forming reactants. All right. That's another way to look at it. So equilibrium if it favors products, then that is the forward reaction, or we say that equilibrium lies to the right, right? If it favors reactants, right, we would say that equilibrium lies to the left. So the opposite is true. So if I say those type of things, then we know that that's the case. All right, so before we can really learn anything, let's go over some things. So we have what's called collision theory, right? Collision theory, what this basically means is reactions must have sufficient energy or position to occur. Right? So kind of like the kinetic molecular theory, they must have sufficient kinetic energy. So they have to hit hard enough to join. Right? So what we say right here is molecules without sufficient kinetic energy simply bounce apart. Right? Activation energy, we talked about that in thermochemistry a little bit. So activation energy is the minimum kinetic energy to start a reaction. Right? So remember, the reactions have to have either sufficient energy or position. Right? So if you remember in biology, right? So biology is an enzyme. You can say that enzymes lower the energy of activation by orientation. Right, by orientation, that's a self orientation. So remember what we said was lock and key. So an enzyme There's a large molecule that holds reactants in the proper position so they fit, right? So this would fit here. So that's what enzymes do in your body. So enzymes lower energy of activation by putting things in the right place, kind of like a Lego going together. In chemistry, since we don't always have large molecules, we kind of have to do it another way. We just simply have to lower the energy, right? And we'll talk about that. So factors affecting reaction rates, temperature, right? So some of these make sense. Temperature. Why does cooking work? Well, cooking works because we raise the temperature and we give each collision more kinetic energy. So temperature increases kinetic energy, right? It gets us over that reaction barrier, right? Increases the amount of collisions per time, and each collision has more energy. Oops. We have concentration, right? Which simply just increases the amount of collisions per time. If you look at the little picture right there, right? If I have more reactants, there's more things bouncing off, and one or more of them will have the proper orientation, which will lower the energy requirement. There's particle size, right? So particle size. Let's try that again. Particle size, which is surface area, right? Increasing surface areas, or making things smaller, increases the area available. So think about it. If I take a sugar cube and I drop a sugar cube in a glass of water, and then I take another sugar cube and I grind it into small pieces and I drop it in an equal size cup of water, the one I grind up dissolves faster because the inside of the sugar cube is exposed to the solvent as well, right? So remember, making things smaller, grinding things up, increases the surface area for the reaction, right? Because now it can get to the spots in the middle. And the last is a catalyst, right? So a catalyst, make sure you know this statement here, lowers the energy of activation necessary for the reaction to proceed. So it precedes the reaction, right? So if you look at this graph here, let me see if I can make this larger for you. I can. Let me see if I can make it. No, I can't make it larger there. All right, let's just move it up. Can't move that. All right. So if you look at this graph at the bottom, right here, right? So we had an original EA. And then we lower that activation energy. So it allows the reaction to occur at a lower energy. And that's called a catalyst. Remember, important things to know about the catalyst is it's not part of the product. I have no idea why it's doing this. So it's not part of the product. Or you could say, it's not working very well. Holy cow. Right? So it's not part of the product, or you can say it's not used in the reaction. So the catalyst, once that reaction is complete, it simply releases and finds more reactants to put together. Kind of like a biological enzyme. Right? Really short, really sweet. And I will post another lecture talking about Le Chatelier's principle. Right, hope you're having a good day. Talk to you soon. Bye.